Hello, my name is Angad and this is my presentation for Midterm 2. I'm a part of Group 8, which includes William and Nan, and for this project, we focused on visualizing graph algorithms. Specifically, I focused on visualizing the graphs algorithm. I do have some experience with the graphs algorithm from the last project, where in that group we implemented it as a game on a grid. For this project, I implemented it on a graph structure. So let's talk a little bit about what the graphs algorithm is basically. The graphs algorithm is a pathfinding algorithm used on grids mostly. Um, but for this project, I implemented on a graph. It's a pretty brute force method where you're checking the neighbors of the node you're currently at. So if we look at this example in the corner here, we have the start node, and we're just basically checking the neighbors all the way until that goal node, and then we can just trace our way back through the numbers. So it's a really local amount of knowledge you have since you only have knowledge about the neighbors. You don't have knowledge about the entire graph or grid. Talking about the complexity a little bit, the complexity is in big O notation is OV, where V is the number of vertices in the graph or grid. And this is assuming that there's no obstacles. So if we look at this example that we were looking at, these black squares here represent obstacles. And obstacles will change the complexity up a little bit. So in this project, I haven't added any obstacles, so the complexity is just OV. And I implemented the string using a queue data structure. So in the worst case scenario, the graphs algorithm has to go through all the vertices. In the best case scenario, the goal could only be one edge away from the start, which is the example I'm going to be using where we have node 0 as a start node and node 4 is a goal node, and they're only an edge away, which is the best case scenario. And basically, I've noticed that on a graph structure, the graph algorithm behaves like like the breadth first search. Um, Basically, the nodes are just the grids, or like the little squares here, and the edges are weightless. There's no weight to the edges, unlike other algorithms. So, but most of the time, the grasp algorithm is not optimal. There are some better algorithms like A star, which can be used. For code implementation, I coded this project in Python on VS Code. I created some functions for the algorithm and user input using the queuing data structure, and basically asks the user for some graph information. So we can see here it'll ask for the number of edges, the vertices for each edge. It returns back the distances from the start node, and then you enter in the goal vertex number. So what goal you want to go to, what's the goal node, and then it returns back the shortest path, which is the least amount of edges basically. So I can show you some of the code here. So basically, I recreate a graph, and then we have the main code right here where we have the graphs for our algorithm. It basically just checks if we visited a neighbor or not, and then it adds it to the queue. And for since we reached the goal node after running the graphs for our algorithm to go back to the start node to find the path, this function here is just going back towards that path, and this is just the user interface. And I wanted to show an example with AI Space, which is a visualization tool. So I will show this example first here, which is example we've been working with. I've set this algorithm to breadth first search since of the similarity with the graphfire algorithm. So if we run this code here, we can see that it found the path from node 0 to node 4, which is what we were expecting. And it expands to all the neighbors, and it found that the neighbor is node 4, which is the goal node, so it was easy to find the path. But I wanted to show another example where there could be two similar paths towards a goal node, and what would the algorithm in this case choose? So if we run this algorithm here, the same algorithm, we can see that it chose node 0 to node 1 to node 3 and not node 0 to node 2 to node 3. And we can try this as many times as we want, and we can see that it'll always return this path over here, the one on the left side for us. And this is because of how the algorithm could be programmed. So basically, when we're inputting all these nodes in here, the node towards the right of node 0, or this node here, is always implemented first, and then this node is implemented after that, which is why the computer or algorithm prefers going to this node and then this node. So that's just a small little example I wanted to show about the algorithm. So if we go back to the slideshow here, talking about the group work, so we divided the work by algorithms, where Nan worked on the Castro algorithm, William worked on A star, and I worked on the Grassfire algorithm. We used GitHub for version control and uploading all our code and our parts. So all our code is available on GitHub. And for communication and helping each other out, we use Discord, and we actively communicated on there. And all other work like the analysis and write up was done on Google Docs, shared document. These are my references I've used, and thank you so much for watching.